Hello again, this is part 7 of chapter 7 Entropy. In part 6, we did some kind of easier problems. So now we are going to go over, additional problems. So the first one we're going to do, it is quite lengthy. So this is problem 750, and it's a very important problem. So this is a super good problem. Steam at 6,000 kilopascals and 500 degrees C enters a steady flow turbine. The steam expands in the turbine while doing work until the pressure is 1000 kilopascals. When the pressure is 1000 kilopascals, 10% of the steam is removed from the turbine for other uses. Like steam has other uses, for instance, in power plants. So you will, those who will take Thermo 2, they will learn it, in more depth. So, all right, so then remaining 90% of the steam continues to expand through the turbine while doing work and leaves the turbine at finally 10 kilopascal. So you see this is below the atmospheric pressure because it enters the condenser, and condenser operates at atmospheric in a vacuum in order to actually give the turbine the chance to expand further in order to extract more work. The entire expansion process by the steam through the turbine is reversible and adiabatic. So the turbine is isentropic. Sketch the process on a TS diagram with respect to the saturation lines. Be sure to label the data states and the lines of constant pressure. So in part A, we want to sketch the process on a TS diagram. In part B, if the turbine has an isentropic efficiency of 85%, we define isentropic efficiency in the lectures. What is the work done by the steam as it flows through the turbine per unit mass of steam flowing into the turbine in kilojoules per kilogram? Okay. So you may want to pause the video and read through the question again to understand it. All right, so let's start with a schematic of the turbine. So this is the turbine from right to left. Point 1, the inlet is superheated. At point 2, some steam is extracted for other purposes. At point 3, the remaining of the steam is expanded all the way to the condenser. The problem tells us to assume reversible adiabatic, so the process is isentropic. So if you want to show it on a TS diagram, so on a TS diagram, this is the two-phase dome. Under the dome, we do have a phase change. So we draw the constant pressure lines, 10 kilopascal, 1000, 6000. So initially, the steam pressure has been at 6,000 kilopascals. So this is the constant pressure line, and point 1 is superheated state. That's where the steam enters the turbine. Then it expands all the way to point 2, and at this point the pressure is 1000 kilopascals. And you see that it is isentropic, so it moves down straight at constant S. And then it continues to expand to point 3 where the pressure reaches 10 kilopascals. So this is the TS diagram of these processes. All right, so the assumption is that the kinetic and potential energies are negligible, so you need to write it down. Then you need to say that for each state, which table you're going to use. So this is table A6. So you're going to use table A6. So this is basically the instructor's solution. So for you in the exams, you need to write much more details because it has to show that you understand it, and it has to show where the numbers are coming from. So therefore at 500 degrees C and 6 megapascal, we go ahead and use the steam table. We read H1. We also write down S1 because we're going to use it. It's an isentropic process, so entropy does not change through from process 1 to 2 and then to 3. Or at least this is the assumption that we make for now. So S1 is read from the table. So how about the state 2? At the state 2, the pressure is given 1 megapascal. So this is a state 2 on this line. And we do need a second property for a state 2 because in order to specify other properties, we do need to know at least 2 properties for a simple compressible substance. So S2 is equal to S1. Now for point 2 could be superheated, could be saturated. But for now, let's assume that it's superheated, and if it's proved otherwise, then we would need to go to the two-phase assumption. So here we do need to use table A6, the steam superheated table. Again, we need to write it down. It requires interpolation. So we need to go to the table and check the section for pressure equal to 1 megapascal. And then in the table, we will look for entropy. So S2 equal to S1, and S1 is known, but it is very unlikely that the table directly provides values for exactly this S2 equal to S1 equal to 6.8826. So an interpolation is needed in order to find H2. We call it H2S because it's based on the assumption of entropy constant. Because the problem is saying that assume the turbine is isentropic. So we need H enthalpy because we want to find the work. Then we move to a state 3. For a state 3, the pressure is known. P3 is known, 10 kilopascals. And again, S3 is equal to S2 equal to S1, based on the isentropic assumption. So usually the exit of turbines is under the dome, is two-phase, because the exit of the turbine is two-phase but very close to the saturated vapor, because we want to extract enough energy or maximum energy from the steam. Therefore, it does not exit while it is still superheated. So it exits the turbine when it is already in the two-phase region, but it is very close to the saturated region. And the reason is that we don't want too much water or moisture in the mixture, because the water or droplets would damage the turbine blade. So therefore, point 3, the exit from the turbines, is usually under the dome, two-phase, but it is very close to the right. So with this presumption, we go ahead and assume that it's like two-phase, and therefore we use table A5, the pressure table. You need to mention that, table A5. And for this case, for this given pressure, For this given entropy, you can go ahead and find H3S first. So you go ahead and based on entropy, S3 is equal to S1 is equal to SF plus X3 SFG. So first you find X3S. We have done it in the previous lecture. And once you know the quality, you can go ahead and calculate H3S. Again, S means it's based on isentropic assumption. So H3S is equal to HF plus H3S times HFG. So here is just the answer here. So okay, so you have all of the H's required in the first law. In the first law, you also need the masses. So m dot 1 is the mass at point 1 at the entrance of the turbine is equal to m dot 2 plus m dot 3. So m dot 2 is 10% of the mass because the problem says that 10% was extracted. So the rest of it, which is 90% of m dot 1, is equal to m dot 3. So I have repeated the TS diagram again so that it helps us better understand the problem. So now we write the first law. Energy in is equal to energy out per unit time. We need to mention that this is a steady flow process. Then for the steady flow process, energy in is equal to energy out per unit time. We also need to mention that the turbine is adiabatic, so Q is 0. We either mention it here or in the beginning of the problem. So energy in is m dot 1 h1. Energy out, turbine work, m dot 2 h2. Some energy is removed when some of the steam is removed, and then the rest of the energy is removed from leaves the turbine at the exit of the turbine, m dot 3 h3. So because we know that m dot 2 is 10% of m dot 1 and m dot 3 is 90%, we substitute these values and then everything in terms of m dot 1 as shown here. So if we want to show the turbine work per unit mass, then we divide all terms by m dot 1. Then that would give us lowercase w out, which is the turbine work per unit mass. So as a result, H1, this based on the energy balance, we do have this, H1, H2, H3, and turbine work out. So we can go ahead and find WS out because H1, H2, and H3 are known. So these are in the previous slide, we showed them as H2S, H3S. So these are known, we just plug in the numbers and get the turbine work per unit mass. The second part of the problem is that now, if we consider the fact that the turbine is actually ideal, it's not isentropic with an isentropic efficiency of 85%, what would be the actual work out? So we would need to multiply the isentropic work by the isentropic efficiency in order to get the actual work out from this turbine. Okay, so this brings us to the end of this problem. This was a very good practical problem on a thermal power plant, that the turbine part of a thermal power plant. All right, so another problem, 775. Air is compressed in a piston cylinder device from 100 kilopascals and 70 degrees C to 800 kilopascal in a reversible adiabatic process. Reversible adiabatic, so it's isentropic. Determine the final temperature and work done during this process. Determine the final temperature and the work done during this process, assuming constant specific heats and variable specific heats for air. So based on two different assumptions. First, assume that specific heats are constant, find the temperature and the work done. Then assume that specific heats are variables and then find the temperature and the work done. So in B, we get a better estimate. It's more accurate than A. All right, so this is the schematic of the problem. So we have a piston cylinder, air in it. It's adiabatic. So we need to write down the assumptions. We treat it as an ideal gas. It's reversible adiabatic. We must write down these assumptions. And for part A says that use constant specific heat. So we need to use the table A1 and A2. So at the right place, I will mention it. So assuming constant specific heats, we can go ahead and use the isentropic relations. T2 over T1 equal to P2 over P1 to the power of K minus 1 over K. So the values of K's are needed. So these are found in table A2. We need to mention that where we found it. So we plug in the numbers and find T2. So this was an isentropic process. We simply used the isentropic relations. We did have the ratio of the final pressure and initial pressure, and also we did have the initial temperature, so we went ahead and found final temperature. So now the next step is to find the work done during this process. So in order to find the work done, we need to write the first law. Energy in minus energy out is equal to delta E. So there is no heat transfer, Q is 0. We need to mention that specifically. So Q minus W, or energy in minus energy out. So if we write it based on Q minus W, then W would be work done by the system. But in this case, work is done on the system. So W itself is negative. So another negative makes it positive. But if we use this form, energy in minus energy out, there is no energy out, and energy in is equal to the work. And it's equal to delta U because kinetic and potential energies were assumed negligible. It's equal to mu2 minus u1. Because in part A, we want to do it based on the assumption of constant specific heats, then it's equal to mcv delta T. So we do know T1 and T2, but how about CV? So during this process, the temperature changes from 290 to 525.3. So in order to find a good approximation for CV, we need to find the average temperature of the initial temperature and final temperature, and then go ahead and use table, I believe it's on table A2. in table A2, you will see CV and CP for different temperatures. Of course, it's not listed for temperature of 407.7. It's listed for the round numbers. So you need to go ahead and do interpolation. So CV at 407.7 by interpolation is found 0.727. So you need to show your interpolation as well. Then with this CV average, you just plug in the numbers and you can find W in. Because we don't have the mass, we find everything per unit mass. So W in per unit mass is CV average T2 minus T1. So that was based on the approximate analysis. So you remember from the lectures, we do have approximate analysis and we do have exact analysis. So this was the approximate analysis. So how about the exact analysis? And so based on approximate analysis, the temperature is 525 and the work is 173.1. So let's see what will happen if we do an exact analysis. Part B. So assuming variable specific heats means the exact analysis. Find the final temperature using the relative. So we're going to use the relative pressure data of table A17. So we need to specifically mention that this comes from table A17. And we need to mention all of these details. These are what you see here. These are the minimum details which are required to be written down. So initial temperature is 290 Kelvin. At 290 Kelvin, if we look at the air table, we see the relative pressure 1.231. So that's the relative pressure. We also need U, the internal energy, in order to find the work. So we write down both of these two numbers. And then we use this exact ratio, P2 over P1 is equal to PR2 over PR1. If you do not understand it, go back to the lectures and lecture notes. So the exact analysis tells us that the ratio of P2 over P1 between two states is equal to the ratio of the relative pressures. Because we have P1 and P2 and we have PR1 from here, we can go ahead and find PR2. 9.849. And this is dimensionless. We need to go back to the air table and look for this number under the PR column. 9.849. If you look at this, you see that 9.8. So it's between these two, between the temperature of 520 and 530. So an interlinear interpolation is needed here again in order to find the exact temperature, which corresponds to 9.849. So it should be in between somewhere here. So if you do the interpolation, T2 becomes equal to 522.4. If you go back to the previous slide, I wrote it down. The approximate temperature that we found was 525. So based on constant specific heat, the temperature which was found was 525. The accurate answer is 522. So this shows that the approximate solution in the previous slide was good enough. So in addition to temperature, you do need to do interpolation to find U, the internal energy as well. So from this column. So based on the interpolation, you find U2, and therefore W in per unit mass is equal to U2 minus U1 equal to 169.25. based on the exact analysis. Based on the approximate analysis, the number was 171. So it's about 1%, a little bit more than 1% difference. Okay, so this is the end of this problem. So of course, for doing interpolation, you would need some additional time. So you will be given, reasonable amount of time in order to be able to do interpolation on all parts, in time. So next problem is 784. We have air at 800 kilopascal and 400 degrees C entering a steady flow nozzle. This is another device nozzle with a low velocity. So it means that it's neglected, can be neglected, and leaves at 100 kilopascals. If the air undergoes an adiabatic expansion process through the nozzle, adiabatic, what is the maximum velocity of the air at the nozzle exit? So maximum velocity, okay, so it's a good question, easy, but still it does have some good points. So maximum velocity means if we assume that the process is not only adiabatic, but it's also reversible. A reversible expansion in the nozzle will result in the maximum work, isentropic process. So this is our nozzle, and we're gonna assume isentropic process to find the maximum work. Maximum exit energy or exit kinetic energy. So the problem doesn't say whether to use approximate solution or to use exact solution to find the condition at the exit of the nozzle. So therefore, if it's not clear, then it's up to you which method you want to use. So here is based on the approximate, but I will tell you. So in the exams, I will specify whether to use exact based on the table. Exact means using table A17 is exact. So A17 is the exact solution, gives you the exact solution based on the relative properties. And whenever you use table A17, you should know that this is exact. So I don't have the right tools here. I need to write using the mouse. And whenever you use CP, CV, CP or CV average values, then that's approximate. When you write like CV delta T for U and CP delta T for H, that's approximate. So in order to find the final temperature at the nozzle exit, T2 over T1 is equal to P2 over P1 to K minus 1 over K. K from table A1, 1.4 for air. We plug in the numbers. The outlet temperature of the air is 371.5 based on the isentropic assumption. So if we write the first law on the nozzle, energy in minus energy out equal to 0 is a steady state. You need to write all of this. Then energy in is equal to energy out. It's adiabatic. Q is 0. It is so I need to write it down. There is no work done during this process. W is 0. You need to mention that. So energy in is therefore due to the enthalpy coming in and due to a kinetic energy which was set to be neglected. It was said that it's low, means that you neglected. And then at the outlet, you have enthalpy of the outlet, and you have kinetic energy at the outlet. So if you rearrange and divide everything by mass flow rate, H2 minus H1 plus kinetic energy at the outlet, because you are following an approximate solution, H2 minus H1 is Cp T2 minus T1. So if you rearrange, you can get the velocity as a function of these parameters. So now the question is that, so you do have T1 and T2, but how about Cp? So for Cp has to be evaluated at average of T1 and T2. So T1 is 273 and T2 is 371.5. So you find the average temperature and then find the average Cp from table A2 for the corresponding average temperature. So then the velocity is obtained as 778.5 meters per second. So that's the maximum possible velocity that could be obtained based on the assumption of the nozzle being isentropic. In reality, because the nozzle cannot be isentropic, so the velocity will be lower than this. Okay. So let me see what other problem we. All right, so this is another problem, 793. Consider a steam power plant that operates between the pressure limits of 10 megapascals and 20 kilopascals. So 10 is the pressure here, inlet to the turbine, and 20 kilopascal is the pressure here, exit of the turbine and inlet to the condenser. I have added a schematic of a thermal power plant as well, so we have talked about it multiple times. Let me explain it one more time. So in the pump, liquid water is pressurized. So at the exit of the pump, we do have liquid water. It enters the boiler. Heat is added in the boiler, for instance, in a furnace using coal or natural gas or nuclear power, any other source of heat. So that's Q in coming to the boiler. It vaporizes the water, generates steam. At the exit of the vapor, we do have a steam at superheated steam. Then at the inlet of the turbine, the superheated steam expands, generates work, and the work is given to the generator. Then at the exit of the turbine, the steam exits the turbine, usually in the saturated state, a mixture of a little bit of moisture and vapor. It's very close to saturated vapor at x equal to 1. It is not exactly x equal to 1, but x, the quality is very close to 1. Then in the condenser, it's like, you can imagine it's like a heat exchanger like this. In the condenser, because we have a water vapor mixture, so we need to extract heat from this mixture in order to condense it, convert it to liquid water, and then the liquid water enters the pump again, and then it's pumped to a higher pressure. So the reason that we need to do this process, because first of all, we cannot remove this part because it's against the second law. It's not possible. Later you will see the cycle for this power plant and understand it better. But for now, in the pump, we can only pressurize a liquid. We cannot pressurize a mixture of water and its vapors. So that's why it has to be liquidified and then introduced to the pump. Okay. So this was an explanation of different components. So we can actually, with the knowledge that you have now, you can analyze all of these components of a power plant. So a steam enters the pump as saturated liquid, Well, steam enters the pump. Well, steam doesn't enter the pump, but saturated liquid enters the pump and leaves the turbine as saturated vapor. So it leaves the turbine as saturated vapor, x equal to 1. So here at the exit of the turbine, x is equal to 1. And at the inlet to the pump, x equal to 0. This is what it means. This is what the problem is trying to say. At point 1 entrance of the pump, you assume that it's like saturated liquid at x equal to 0. So determine the ratio of the work delivered by the turbine to the work consumed by the pump. Assume the entire cycle to be reversible and the heat losses from the pump and the turbines to be negligible. So it means that the turbine is isentropic and the pump is also isentropic because there is no heat loss and there is no irreversibility. This is a super good problem. So this is the pump, the component, pump component, and this is the turbine. So we give them number 1, 2, 3, 4 in order to prevent, confusion between, enthalpies and other properties. So kinetic and potential energies are negligible. We need to write it down. And the process is reversible in the turbine and in the pump. And they are also adiabatic. Therefore, the pump and the turbine are isentropic. We must write these assumptions down. Okay, so then we need to find the properties because we want to find the work of pump and work of turbine. So we need to know the properties at the inlet and outlet. And by properties, it essentially means we need an enthalpy because when we write the first law, the enthalpies appear. So we do need to find enthalpy. So we can start from any point that we wish. Let's say we start from point 4. At point 4, the pressure is known, 20 kilopascals, and it's saturated vapor. So x equal to 1. So saturated vapor means x is equal to 1. Therefore, H4 is equal to Hg. And S4 is equal to Sg because it's saturated vapor. If we show it on a TS diagram or PV diagram, at point 4 exit of the turbine, we are looking at this point. Inlet, so the turbine inlet is like somewhere here. This is point 3. And point 4 would be some point like here. And then point 1, which is inlet to the pump, it's like here, it's saturated liquid. Okay, so point 3, it's inlet to the turbine, it's superheated steam. So the pressure is given, but nothing else was given. However, we know that the turbine is isentropic, therefore its entropy should be the same as the entropy at point 4. So S3 is equal to S4. So this comes from table A6, and you must mention it, and this comes from table A5. The pressure table, saturated water pressure table. So with this 10 megapascals, you need to go to 10 megapascal section and then look for this entropy S3 equal to S4 equal to 7.9. So you cannot find this number there, so you will need to do interpolation. So need to do interpolation here. So interpolation, linear interpolation in order to find the enthalpy of point 3. You must write the details of your interpolation here. Okay, so for point 1, the end inlet to the pump, we know that it's saturated liquid, so V1 is equal to Vf at 20 kilopascal, because this line is the 20 kilopascal constant pressure line. So V1, the specific volume of the water at the inlet to the pump, which is reciprocal of the density of water, is known. If you reverse it, it's almost 1000 kilogram per cubic meter density of water. So that's all we can find based on the given information. So let's see if with this given information we can find the pump work and turbine work. If we write the first law of thermodynamics for the pump and turbine, both of them E dot in equal to E dot out, both of them steady flow devices. We need to write this down and tell that it's a steady flow process. Then we need to say that heat transfer is 0. Q dot is equal to 0. Sorry about the mess. So Q dot is equal to 0. So energy in the turbine is m dot h3. Energy out is some work which is generated plus the energy of the steam that leaves the turbine, m dot h4. If we divide it by m dot, so we can find the work per unit mass, which is equal to h3 minus h4. So that's the value. So then for the pump, we can write the same equation for the pump. This equation in energy in equal to energy out is valid for the pump as well. However, for the pump, we don't know the enthalpy of the outlet of the pump for now. Instead, we know that we found the work of steady flow devices, and we said that the work of the steady flow devices is equal to the minus integral of VdP plus change in the kinetic energy and potential energy, which are negligible. So the pump require the pump input, the work input to the pump is simply integral of VdP. And since we are dealing with a liquid, V is a constant, so this integral becomes V1 P2 minus P1. We do know P1, we do know P2, so we can go ahead and find the pump work based on this equation. So now if we go back to the, for the pump, if we go back to the energy balance or first law, so the pump work for the pump, if we write H1 based on the first law, H1 plus W of the pump, so plus W of the pump, and there is no heat transfer, this is equal to H2. If the problem asks you to find H2 as well, then now you can say that H2 is equal to H1 plus WP. All of these are per unit mass, and this is based on the first law, similar to the turbine. So we didn't use this equation, but this is another equation that can be used if the problem, for instance, had asked for H2 as well. So the last step is to find the ratio of the pump work to turbine work, or turbine work to pump work. If we plug in the numbers, the ratio is 206. The ratio of the turbine work with respect to the pump is very large. 206.7. The turbine work is much larger than the pump work. Okay, so let's stop here. At this point, we did some very, very important and practical questions in this lecture. Please make sure you go over and understand all details. Don't forget to do the textbook examples. The examples of the textbooks are within the best for you to understand the concepts and understand what type of problems are important. So in another lecture, we will go ahead and do several additional more problems. Thank you for watching.